Hi everybody. In this section, we're going to look at areas again. Now, the title of the section in the textbook is Area of Regions in the Plane. But specifically, what we're going to be looking at is how to find the area between two curves. To start out, let's remember how we defined the area under a curve and above the x-axis as the limit of a Riemann sum. Back then, we said we wanted to find the area under a curve and above the x-axis between two x values. And what we did was we used rectangles to approximate the area. We started out with one giant rectangle. That gave us way more area than was actually under the curve. So we said, how about if we split this up into two rectangles? Now the stuff sticking up above the curve isn't so much. So using the areas of the rectangles as an approximation of the area under the curve was a better approximation. And then we noticed that if we used three rectangles, we got an even better approximation. So finally, we defined the area under a curve and above the x-axis to be the limit of the sums of those rectangles. We called the sum of the rectangles a Riemann sum, and so we defined the area to be the limit as n goes to infinity of the Riemann sum. Remember, n was the number of rectangles. And then we had a theorem that said that the way to actually calculate that limit, in other words, the way to actually calculate that area, was with a definite integral. We're going to be doing something very similar in this section. We're going to take the region that we're interested in and cover it approximately with rectangles. Notice that the left corners of each rectangle are on the curves. So I've just drawn a few rectangles, and of course they continue, and we're going to say we have n rectangles. Now, what's the area of each rectangle? Let's pick a generic rectangle. I'm going to grab the second one because I can see where it is, but let's think of that as rectangle number I, because I want to be generic here. The x-coordinate down here then would be x sub I. What's the height of that rectangle? Well, it goes up to the top curve, and the y-coordinate or height of the top curve there is f of x sub I. The bottom edge of the rectangle is at g of x sub I. So, computing the area, we have the height, which would be the difference of the height of the top of the rectangle minus the height of the bottom edge of the rectangle. So f of x sub I minus g of x sub I. That's our height of that generic rectangle number I. Now, what's the width? To get the area, we need to multiply the height by the width. What's the width? Well, remember, we called the width of each rectangle, they're all the same width, we called that delta x. The sum of the areas of the rectangles approximates the area of the region. The region we want, that region that's pink in the picture. We called the sum of the areas of n rectangles, we call that R sub n, that's a Riemann sum. That would be the area of the first rectangle, f of x1 minus g of x sub 1 times delta x plus the area of the second rectangle, which would be the height is f of x sub 2 minus g of x sub 2 times the width, delta x, so on and so forth, until you get to the last rectangle, the rectangle number n, which is going to have height f of x sub n minus g of x sub n times delta x. So the actual area of the region we define as the limit as n goes to infinity of R sub n. That's the limit of the sum of the rectangular areas as we take more and more and more rectangles, so they're skinnier and skinnier, and they look more and more like the region we're covering with them. Finally, we said that the way we could calculate that limit was with the definite integral. That would be the definite integral from a to b of f of x minus g of x. The subscripts go away when you're writing the definite integral, and the delta x is represented with a dx. So there's our area between two curves. If f and g are continuous functions with f of x greater than g of x, that just means that f is on top of g. And we're interested in the region between x equals a and x equals b. Then the area between them and between a and b is given by, as we just said, the definite integral from a to b of f of x minus g of x dx. And I really want to emphasize that the names f and g don't really mean anything. In other words, in a problem that you're doing in the homework, you can't assume that f comes first just because it's named f. You have to have the curve that's on top coming first. So maybe a better way, not so mathematical, but maybe a better way would be to write that we have the definite integral of the upper curve minus the lower curve dx. And don't worry, I'll show you in the examples how to figure out which one comes first. We'll do that in the next video.